Our modern world runs on lithium-ion, but we have officially hit a dangerous physical ceiling. Smartphones that overheat and electric vehicles that take hours to charge are symptoms of a century-old design.
The solution isn't just a better battery. It is a total reimagining of how atoms move through matter. Welcome to the era of the solid-state battery, a breakthrough that promises to double range and eliminate fire risks forever.
In this investigation, we deconstruct the atomic struggle between liquid and solid energy storage.
We are about to witness the most significant leap in power density since the dawn of the electronic age. To understand the future, we must first look at the flaw inside every battery you currently own. Every standard lithium-ion battery contains a flammable, volatile liquid electrolyte that carries ions between electrodes. This liquid is the battery's greatest strength, allowing for easy ion flow, but also its fatal weakness.
Under high heat or physical impact, this liquid can ignite, leading to a violent process called thermal runaway.
Furthermore, liquid electrolytes allow for the growth of dendrites, microscopic, needle-like metallic structures.
These dendrites eventually pierce the separator, causing an internal short circuit that can lead to an immediate explosion.
Enter the solid-state design, where the dangerous liquid is replaced by a stable, solid ceramic or polymer layer. This single change allows engineers to remove the bulky separators and safety cooling systems required by liquid batteries. By removing the dead weight, we can pack significantly more energy into the exact same physical footprint. The physics of ion conductivity in solids is much more complex than in a free-flowing liquid medium. Ions must hop through a rigid crystal lattice, a process that requires precision-engineered atomic tunnels. Chemists are now using sulfides and oxides to create these paths, allowing ions to move at near-liquid speeds.
This breakthrough allows for ultra-fast charging, as the solid layer can withstand much higher current densities without degrading.
Imagine charging an entire long-range electric vehicle in less time than it takes to fill a tank of gas. Because there is no liquid to catch fire, these batteries can operate safely at much higher internal temperatures.
This eliminates the need for heavy, complex thermal management systems, further increasing the vehicle's overall efficiency and range.
The most exciting potential of solid-state tech is the ability to use a lithium metal anode. In current batteries, the anode is made of graphite to host the lithium ions safely within its layers. But a solid electrolyte is strong enough to handle pure lithium metal, which has the highest energy density of any material.
Switching to lithium metal could boost the energy capacity of a battery by over 50% in a single step. However, the interface between the solid electrolyte and the solid electrodes is a massive engineering nightmare.
As the battery charges and discharges, the materials expand and contract, causing them to physically pull apart over time.
If the contact is lost, even at a microscopic level, the flow of electricity stops and the battery dies.
Engineers are using high-pressure manufacturing and self-healing polymers to keep these layers pressed together during operation. The cost of producing these specialized ceramic layers is currently 10 times higher than traditional liquid-based manufacturing.
Scaling this technology from a small laboratory sample to a mass-produced car battery is a global industrial race. Major automotive giants and tech startups are investing billions to build the first gigafactory for solid-state power. The first generation of these batteries is already appearing in high-end electronics and niche military applications today. Within the next decade, this technology will likely trickle down to every laptop, drone, and smartphone on Earth.
We are moving away from the era of volatility and into an era of stable, dense, and nearly eternal power.
Solid-state batteries don't just last longer, they can survive thousands more charge cycles than their liquid ancestors.
This makes the total life cycle of an electric vehicle much more sustainable for the planet's long-term health. The reduction in rare earth metals required for cooling and housing also lowers the environmental impact of mining. We are currently in the Silicon Valley moment for energy, where a single breakthrough will change everything. Quantum simulations are being used to discover even more efficient solid electrolyte materials that we haven't dreamed of yet. This is a battle of material science, fought at the scale of individual atoms and electrons. The winner of this race will control the energy infrastructure of the 21st century and beyond. Every second, researchers are testing new combinations of solid glass and ceramic to perfect the ion path. The goal is a battery that is as safe as a block of wood, but as energetic as a tank of jet fuel. This shift will finally make electric aviation a reality, as weight is the primary enemy of flight. High-density solid-state cells could provide the power-to-weight ratio needed for commercial electric regional jets. This would decimate the carbon footprint of the travel industry, moving us toward a truly green global economy. But we must be patient, as the physics of solids cannot be rushed by venture capital alone. Stability at the atomic level requires perfect manufacturing conditions, free from even a single speck of dust. A single impurity in the ceramic layer can create a bottleneck that leads to localized overheating and failure. This is why cleanroom standards for battery factories are now rivaling those of semiconductor microchip plants.
The transition will be slow at first, then happen all at once, just like the shift from Clydesdale horses to cars. Legacy battery companies are scrambling to pivot their entire supply chains to accommodate this radical new architecture.
The geopolitical map of energy will be redrawn based on who owns the patents to these solid electrolytes. It is no longer just about who has the oil, but who has the smartest atomic engineers. In the future, dead batteries might become a relic of the past, as solid cells retain their charge for years. This would revolutionize emergency backup systems for hospitals and deep space exploration probes alike. The Voyager probes of the future will be powered by solid-state tech that can survive the cold vacuum of space. We are witnessing the end of the liquid age of energy storage and the birth of something much more permanent. Every time you charge your phone in the future, remember the microscopic hopping of ions through a solid crystal. It is a dance of physics that allows us to carry the power of lightning in the palm of our hand.
The safety, speed, and power of the solid-state revolution are no longer a matter of if, but when. The final hurdle is cost, and history shows that mass production always wins against high prices eventually.
As the prices drop, the world will undergo a total electrification of everything, from lawnmowers to cargo ships. This is the silent engine of the future, working without noise, without flame, and without limits. The physics of the solid-state battery is the key that finally unlocks the full potential of renewable energy. Do you think the promise of unbreakable batteries will finally convince the world to abandon fossil fuels forever?